Quantum Chymistry, a short essay by Bruce Mills, otherwise known as the obligate pedestrian. One way to make a cake is to put some flour in a bowl and then add eggs and milk and mix until the batter looks and feels right. Another way is to measure each ingredient carefully by weight and volume, mix for precisely a given time, best done using an automated mixer. In a strong sense, the first method is traditional alchemy and the second method is classical chemistry, at least pragmatically as things worked out historically. The chemistry method sounds more objective. It certainly can be learned from a book once the basic equipment and skills have been obtained. The second method requires apprenticeship or a lot of personal study and experience. But in making a cake in practice, the flour can be of varying consistencies and the eggs can be different sizes. They can also be more or less fluid. The measurements do not actually provide repeatable conditions. Commercial bakeries get around this by homogenizing the ingredients and also by only using recipes that succeed under the industrial approach. A recipe that does not is discarded, not because it does not work, but because it cannot be part of an industrial process. Likewise with industrial chemistry. However, the best cakes are made by a skilled practitioner of the first method who can understand the ingredients and add a bit more milk or water or another egg, who mixes not for a given time but until the batter looks and feels right. This is all the more important when the ingredients are not going to be entirely consistent themselves. Traditional alchemists, the good ones anyway, had much more skill in the laboratory. The modern chemist has much more equipment and much more homogenized reactants commercially available on the shelf. This is the source of the claims that alchemy does not work. It does not survive the industrialization process. To get alchemy to work, you have to have alchemical training, not chemical training. Chemical training can actually reduce the chance of getting alchemy to work. As alchemy in the traditional sense gave way to chemistry in the industrial sense, the topic became much more arithmetical. Instead of adding ingredients until the condition was correct, one adds a measured quantity. It works or it does not. Set and forget, plug and play. There are no adjustments to be done or even possible. Instead of the qualitative knowledge of the exact colour or smell, there is the quantitative, that is, numerical skill in measuring weight, volume, temperature and time. Chemistry was taken over by physics starting around 2 centuries ago, and physics by mathematics 2 centuries before that. Much of classical chemistry can and was understood in traditional manner. One can understand classical chemistry in terms of a table of elements and a grouping into kinds based on engagement in standard reactions. A bit of hard slog will do it, but by the mid-19th century there was electromagnetics and thermodynamics in the practice of chemistry, and both are highly mathematical. This is why modern chemistry is much more mathematical than traditional alchemy or classical chemistry, and this is why, in starting to discuss the history of chemistry in the 19th and 20th centuries, some mathematics is going to creep into the story. I will try to be as gentle as possible and to go no further than basic arithmetic and secondary school algebra in this essay. Modern chemistry is built around quantum chemistry. One big distinction is that in classical chemistry the list of elements is basic given data, but in modern chemistry, the deep core, that list of elements is derived mathematically from quantum electromagnetic first principles. Even melting something by exposing it to the heat from a fire involves the principle of radiation of a mysterious something from the fire to the material being melted. Changes in materials did not require direct contact. Also, blacksmiths used the colour of a hot metal as proxy for temperature. Homburgers are blacksmiths around 1680 hitting iron to make it red hot just from hitting, but in this action they used the colour of the iron to determine their progress. Joseph Moxon, 1627 to 1691, was an English printer specialising in mathematical books and maps. Among other books were Moxon's Mechanic Exercises, which included a volume, Doctrine of Handiworks as applied to the arts of smithing, joinery, carpentry, turning and bricklaying, as follows. Of the several heats smiths take of their iron. There are several degrees of heats smiths take of their iron, each according to the purpose of their work. At first, a blood red heat, secondly, a white flame heat, Thirdly, a sparkling or welding heat. The blood-red heat is used when iron hath already its form and size, as sometimes square bars and iron plates, etc., have, but may want a little hammering to smooth it. Use then the face of your hand hammer with a light flat blow, hammer down the irregular rising into the body of your iron, till it be smooth enough for the file, and note that it behooves a good workman to hammer his work as true as he can, for 1/4 of an hour spent at the forge may save him an hour's work at the vice. End of quote. At least in principle in the 20th century, and much more in practice in the 21st century, mathematical computation of the properties of molecules is used. The process is mathematically more sophisticated than the calculations required to land a spacecraft on the moon. And before quantum, there was already much work using classical electromagnetic theory as well as classical and then kinetic thermodynamic theory, none of which can be understood with a lookup table. This is not to say that it was an entirely new component of chem. Heat and light and fire had been used in alchemy, cookery and metallurgy from the beginning. A candle produces light from a chemical reaction. In the 19th century terms, heat is random motion of atoms, and in 21st century terms it is thus a measure of the energy in the quantum states, which is stored in the quantum electrodynamic fields. In 1669, Henning Brand discovered phosphorus that emits light spontaneously. Radiated heat is a form of light, as developed by Herschel circa 1800, who found that there was a calorific light just beyond the visible red in the spectrum of the sun. Humphrey Davy discovered potassium using electricity in 1807. That and the voltaic pile circa 1799 meant that the 19th century theory of chemistry involved the theory of electricity right from the start. Circa 1859, Gustav Robert Kirchhoff, a German physicist, and Robert Wilhelm Bunsen, chemist, inventor of the Bunsen burner, showed that spectral lines are characteristic of each element. This made the study of light a fundamental tool for studying the composition of matter. And there was the spectrum of atoms, bars of light or dark in the light reflected from or passing through a material and refracted through a prism. This is just a more sophisticated way of talking about the colour of the material. It was the core motivation for the development of the old quantum theory, starting with seminal papers by Max Planck in 1900. In the 17th century, the prism was known to give a physical order on the wall: red, orange, yellow, green, blue, purple. Herschel added infrared at the start in the year 1800. The colour of the hot metal shifted from infrared to red, so to orange, and so on, eventually glowing white. This was explained by saying that the relative colour was the same but shifted up the spectrum like the same music can be played an octave higher. We were only able to see a very thin section of this shape. By the end of the 19th century, the principle had been developed of a black body, that many materials radiated the same relative colour shifted up the spectrum as revealed by a prism. The shape of this spectrum was called black body radiation. The law for the peak frequency as a function of temperature was determined by Wien in 1893. In October 1900, Planck showed his formulation of the spectrum to a meeting of the German Physical Society. It was generally accepted as correct, but Planck improved it and tried again in December. It was considered entirely correct, but Planck had misgivings about it for the rest of his career. He introduced the idea that the oscillators in the object could not absorb energy continuously, but rather only in discrete amounts that were proportional to the frequency of the oscillator. That constant of proportionality is known as Planck's constant. It is symbolized by an H. From On the Theory of the Energy Distribution Law of the Normal Spectrum, Planck, Correspondence of the German Physical Society, Volume 2, 237, 1900. We consider, however, this is the most essential point of the whole calculation, E to be composed of a very definite number of equal parts, and use, thereto, the constant of nature, h, it was 6.55 times 10 to the minus 27 erg seconds. This constant, multiplied by the common frequency nu of the resonators, gives us the energy element epsilon in ergs, and dividing E by epsilon, we get the number P of energy elements, which must be divided over the n resonators. If the ratio is not an integer, we take for P an integer in the neighbourhood. End of quote. The question then became how to explain the light, which Homburg identified as being the element of fire, that is given off by different materials. The eventual answer, as given in the 21st century, is that the chemicals are made from positive and negative electricity, and the excited electricity glows because light is electromagnetic radiation. But the details of the way in which positive and negative electricity interact required quantum theory. There are several kinds of quantum theory: Born, Bohr, de Broglie, Heisenberg, Schrödinger. But around 1929, at the Solvay Conference on Quantum Theory, the division was created between the old and the new, between Bohr and Heisenberg, for example. Curiously, this was about the same time that the division was created between the old and the new relativity theory, though not by that name, at the Mount Palomar seminar. Note, photon theory and alchemical corpuscular theory are related. See also the mollusk principle of Einstein. This essay on quantum chemistry is about the semi-classical atomic theories coming from the electromagnetics and quantum mechanics. Quantum alchemy would look more like quantum field theory. This starts to open the topic of valence, orbitals, orbits, and quantum theory. There is definitely some mathematics in that. An atom is, in one view, negatively charged electrons orbitaling a positive charged nucleus. My coinage here, orbitaling, is to indicate that the electrons take up some pattern of behaviour around the positive nucleus without making any claims about whether it is a circle, an ellipse, smeared out, or stochastic. The 21st century view is that the nucleus is made of positive protons and neutral neutrons. The electrons are bound to the protons by exchange of photons. The protons and neutrons are bound to each other by a Velcro-like force called the strong force. This is a naive picture, but it's a very good basic scenario to bounce ideas off. Relating this back to the four elements, earth, water, air and fire, Homburg concluded the element of fire was essentially light. There is some justification for this in that fire involves release of electromagnetic energy into plasma and emitted light. In a plausible sense, bonds in atoms are stored light that is released during an exothermic reaction. The idea of an electron might have been coined by Richard Lemming circa 1840, who proposed the idea of an atom being a core of matter surrounded by subatomic particles. This was followed by the Irish physicist George Stoney, who suggested quantization of charge in 1874 and coined the term electron in 1891. Originally he called it the electrine. Stoney proposed that a fixed amount of charge was transferred per bond in a chemical reaction. Stoney, 1894, of the Electron or Atom of Electricity, Philosophical Magazine, Series 5, 38, pages 418 to 420. Actually, Stoney begins with a comment. Gentlemen, Professor Ebbett, in his paper on the heat of dissociation in last month's September's Philosophical Magazine, says on page 332, von Helmholtz, on the basis of Faraday's law of electrolysis, was the first to show in the case of electrolytes that each valency must be considered charged with a minimal quantity of electricity, the valency charge which, like an electrical atom, is no longer divisible. End of quote of quote. The point that Stoney is making is that the charge on an electron is a unit of charge supplied by nature, rather than being an arbitrary amount. He also refers to Maxwell of velocity, or the speed of light, and the Newton of gravitation, or the gravitational constant. However, Stoney then quotes both himself from 1874 and Helmholtz from 1881, claiming priority. In my opinion, given the quotes, Stoney had the better claim. In brief, Stoney says that electricity is quantized because in an electrochemical reaction the current generated is proportional to the number of atoms used. Helmholtz says that since there are atoms of material, the charge is stored in the atoms, there must be atoms of electricity. I would shore up the claim of Stoney by the Avogadro law, that is, that the number of atoms of material can be counted by the volume of gaseous substance. This allows for, up to an unknown multiple, the number of atoms being used in a reaction to be computed. Stoney actually mentions this explicitly on page 420. Stoney says, for each chemical bond which is ruptured within an electrolyte, a certain quantity of electricity traverses the electrolyte, which is the same in all cases. While it seems that Stoney was quite prescient in his assertions, it does not seem to me the argument was entirely sound, just more of an educated supposition that turned out well. Stoney also says that the spectrum of the atom is due to this atom of charge moving about in the material atom and hence radiating according to Maxwell electromagnetics. He relates the spectrum to a Fourier series of the motion of the electron. Arguably he's not too far off, except the terms are solutions to the Schrödinger equation or the Dirac equation rather than sinusoids, but in a generalised sense the idea does work. Thomson famously isolated electrons in a cathode ray in 1897, only a few years later. Gilbert Lewis, 1875 to 1946, is often credited with the electron bond concept in a paper published in 1916. This arose from the valence theory, which predated the quantum theory of orbitals. In some interpretations, valency and orbitals are strongly related concepts. This led Lewis to define an acid as a material that would accept an electron and a base as something that would donate one. It is subjective, but in my reading, Stoney pretty much got the idea in 1881. The issue of who originated an idea often comes down to who first phrased it in a certain way that resonates with modern ears. Niels Bohr was a very strong influence in quantum mechanics during the formative period, say 1910 to 1940. He ran the Copenhagen School, funded by the Danish government. In my opinion, much of what Bohr said was philosophy rather than physics. In a discussion of problems in understanding the behaviour of atoms in magnetic fields, Atoms, Physics and Human Knowledge, Discussions with Einstein, page 37, the way to clarification of this situation was indeed first to be paved by the development of a more comprehensive quantum theory. A first step towards the goal was recognised by de Broglie in 1925 that the wave-corpuscle duality was not confined to the property of radiation, but was equal and unavoidable in accounting for the behaviour of material particles. End of quote. And a bit later, Bohr says, the new line was pursued with greater success by Schrödinger, 1926, who in particular showed how the stationary states of atomic systems could be represented by proper solutions of a wave equation, to the establishment of which he was led by a formal analogy originally traced to Hamilton between mechanical and optical problems. End of quote. Later, on page 84 of Atoms and Human Knowledge, Bohr, although atomic ideas have contributed more and more fruitfully to the development of physics and chemistry since the Renaissance, they were regarded as hypotheses right up to the beginning of this century, the 20th. End of quote. Bohr then goes on to talk about the contributions of Planck and Rutherford. It is noted that Bohr was a graduate student of Rutherford and brings up the issue that no configuration of classical electromagnetics could explain the stability of the atom. The argument is that for an electron to orbit it needs to accelerate, and to accelerate it needs to radiate, and to radiate it needs to lose energy, and hence the atom will collapse. This issue is often presented as a killer blow for the classical electromagnetism and the need for a quantum theory of atoms. It is not that simple. Steady current does not radiate. For example, a spinning loop of charge will not radiate even though it is accelerating charges. This apparent paradox is resolved by considering the idea of one electron, then two half-size electrons, then 4, 8, and so on. As more are added co-orbiting, the radiation from the one is absorbed by the others, and the total radiation actually drops to zero. To orbit is to accelerate, and to lose energy is to collapse, but the link between the two is that to accelerate is to radiate, which net total is shown to be incorrect. The electron is emitting and absorbing radiation. It is losing and gaining energy. These are forms of self-forces which are rather badly understood even in the early 21st century. There is also the work of stochastic electrodynamics. The principle is that if an atom is immersed in a background of radiation, then it will pick up energy from that background. If it radiates due to acceleration and starts to drop towards the nucleus, it might yet also absorb from the background and rise again. What is the total impact of this complicated interaction? The conclusion of stochastic electrodynamics, mathematically and numerically, is that it ends up in some kind of probability cloud around the nucleus that is very similar to the proposed quantum mechanics. This above should not be read as a debunking of quantum mechanics. The point is that to push the subtle but important principle, it is not actually obvious that classical electrodynamics and classical stochastics are incapable of modelling the atom. Quantum theory is relatively simple and has been very successful in practice. All that is said here is that there is no single killer blow that made classical wrong and quantum right. Getting back to Bohr and the Bohr atom. Rejection of the light quantum, The Dark Side of Niels Bohr, by Louis Boyer, open lecture presented at the 4th workshop on rigged Hilbert spaces and resonance, Spain, June 2001. Abstract. Evidence is recalled of the strong opposition of Niels Bohr at the time of the old quantum theory to the Lichtquanten hypothesis of Einstein. Some episodes with H.A. Kramers and J.C. Slater and W. Heisenberg are recollected. Bohr's changing point of view is traced back to some philosophical antecedents and to his endeavour to deduce quantum results from the correspondence principle. Some consequence for the future interpretation of quantum mechanics, specially to the complementary principle, are considered. On page 3. The irony was, of course, that the difficult Sommerfeld fine structure formula was one of the big successes of the old quantum theory, an issue in which Bohr, failed. He did not apply relativity to the circular orbits only. Sommerfeld never got the Nobel Prize, to the surprise of many, including A. Pace, an admirer of Bohr. Actually, Bohr never recommended Sommerfeld to the Swedish Academy, whereas his recommendees did get the prize normally. Quoting Kramers, the theory of light quantum might be compared with a medicine which will cause the disease to vanish but kills the patient. The fact must be emphasized that this theory is in no way sprung from Bohr theory, to say nothing of its being a necessary consequence of it. Kramers, Holzbook, 1923, page 7. After Compton, Simon and Booth-Geiger experiments, spring 1925, Bohr renounced the statistical-only conservation of energy and momentum, but he does not embrace the photon. Heisenberg says he believed around early 1925 Bohr was the only notorious physicist unbeliever about photons. Bohr's conclusion instead was one should renounce to a space-time description of physical atomic phenomena. Bohr took the correspondence principle as a guide. He had already extracted the, perhaps unwarranted, conclusion that every description of natural process must be based on ideas which have been introduced and defined by classical theory, 1923, A. Pace, Niels Bohr Times, Oxford, 1991, page 230 or page 300. Bohr also opposed the modern quantum electrodynamics, I do not know why, with the result that Tominaga, Schwinger and Feynman received the Nobel Prize, 1965, after Bohr died. Niemann and Kirsch, The Particle Hunters, Cambridge, 1986, page 78 of the Spanish edition. End of quote. And from the actual Particle Hunters by Niemann and Kirsch, page 59 of the English second edition of The Particle Hunters by Niemann and Kirsch, the theory called quantum electrodynamics, QED for short, was put forward by 3 physicists working independently. The Japanese Sin Itiro, meaning firstborn, Tominaga, and the Americans Richard Feynman and Julian Schwinger. The theory aimed at presenting the proper quantum treatment for electromagnetic fields and electric charges, and were based on an idea proposed by Dirac in 1927, to treat the electromagnetic field itself not as a continuous quantity, but as something composed of discrete entities or quanta. At the same time, the electron wave function is also treated as a field. The theory manages to overcome some mathematical difficulties that withheld the development of the basic idea for some 20 years and was very successful in predicting experimental results. Even today, it is considered to be the most precise existing scientific theory. It is interesting that Dirac himself regarded the new theory with suspicion, just as Einstein had received quantum mechanics. Feynman, Schwinger and Tominaga shared the 1965 Nobel Prize in Physics. They could possibly have been awarded that prize several years earlier, but Niels Bohr also suspected the new theory, and his negative attitude towards it deterred the Nobel Committee from acknowledging it. The decision to give the Nobel Prize to the authors of QED was made only after Bohr's death. When it was published, Oppenheimer, the father of the atomic bomb, was in Israel as Niemann's guest. He sent Feynman a telegram from Tel Aviv with only one word, enfin, or at last, in French. End of quote.